Hi, Chase.
Hello?
Yeah, how you doing today?
Fairly well.
Okay. Okay, I got these 6 documents. 1 through 6. Is there a particular place you want to start? I think we've done some of these.
Yeah, some of these we have done, and actually, because this is the last time I'll talk to you before my final, this test she'll go through and she'll send back to me with what I did wrong. So last week I sent you chapters 2 and 3 test, and I'd like to go over the chapter 3 test with you today.
Okay. Is that in one of these 6 documents, or do I need to go back to my email and re-grab that?
You should probably have to go back to email and re-grab that. I could go see if I could send it again to you.
No, that's all right. No, I'll have it. I use Gmail. So you sent this to me on the 7th, right?
Yes.
In fact, I normally save these, but I don't know what I would have called it, so... Chapter 3?
Yes.
Are we potentially going to want to do Chapter 4 also, or should I grab it?
If we don't get to Chapter 4, that's fine. I don't know if we will be able to.
Well, let me pull it up here. Just so I'll put it on my screen, and then I can close out my inbox, which makes everything run a little smoother. Let me close this out. You want to pick and choose the ones you got wrong, or?
I was working on it, so the ones I was having issues not understanding, I think would be the best ones to do.
Okay.
So this is going through my physics. So I guess number 2.
Okay.
On this. Be a good place to start.
Okay. When we're looking for the equation of the tangent line, the most important thing is slope. So let's find slope of this function. So if y equals e to the x times natural log of x, what's y prime?
That's why I had issues, is I wasn't sure.
Okay, let's use the product rule.
So the product rule is the first term times the derivative of the second term plus the second term times the derivative of the first term, right?
Yes.
Okay, well then, so we'd go e to the x times, that was what I got,
The derivative of natural log is 1 over x.
Write that down so I remember that. Okay, plus ln x times e to, I thought you just left e to the x as e to the x.
Yeah, in other words, the derivative of e to the x is also e to the x. Okay? So, if this is equal to f prime of x, what is f prime of 1?
We have e to the 1 times 1 plus the natural log of 1 e to the 1 times e.
What's the natural log of 1?
I don't know. Natural logs I don't quite understand there.
Okay. 0. And it's 0 because the log of 1, no matter what the base, is always 0. Because when I say the log of 1 base b, well, b to the 0th power is equal to 1, no matter what b is. It could be base 100, and it would still be the log base 100 of 1 is 0.
Okay.
So f prime of 1 equals 0. That means our slope of this function is e. And let's use the point slope formula. What's the general point slope formula?
Point slope, is that y equals mx plus b?
That's slope intercept.
Oh, point slope formula is the
reason point slope.
The
reason point slope is better to use here is because we have a slope and we have 1 point.
Yeah, so that's y minus y1 equals m plus slope x minus x1, right?
Now we know what x1 is. What's y1? In other words, x1 equals 1. We have to fill in that to come up with y1.
Will we put the x back into the first equation to find y1?
Yes.
So that's just 0.
Yes. Okay, so now what's our equation?
We have y equals m...
Which is e.
Oh, yeah, equals e x minus 1.
Which is equal to ex minus e. Although I'm betting that they put that on the answer right there.
Yes, they did.
Yeah. C. Do you know the answers to these? Do you have an answer key?
No, I do not have an answer key.
Okay. It's always nice to be able to check, but that's okay. We did it right. Let's have a bigger look at this. Almost prefer not having the multiple choice answers. It's not really an advantage having multiple choice in these.
Yeah.
They might as well be fill in the blank because you can't. You have to answer the question and then find that answer on the multiple choice. So,
yeah.
All right. So take the second derivative. We just take the first derivative and then take the first derivative again. So y prime, the first derivative, the derivative of the outside times the derivative of the inside.
So the derivative of the outside of log is 1 over 4x plus 1
and the derivative
times 4.
So there's y1.
And now we have to do the quotient rule.
Right. So
we have so just to make sure I'm clear here.
Okay, let me give you a way to memorize the quotient rule.
I know what it is, but I was confused on if it was the bottom, if it was the bottom times the top, the bottom times the derivative of the top minus the top derivative of the bottom, or if it was the other way around.
Right, and that's why if you remember this thing, you'll never forget it. Start with the bottom, end with the bottom squared.
Okay. So it's 4x plus 1 times 0 minus 4 times 4 over 4x plus 1 squared.
So this is minus 16 over 4x plus 1 squared. Probably the answer they're going to have. You see why starting with the bottom and ending with the bottom squared, you can't really mess up the numerator. As long as you remember that it's subtraction. Because it tells you that this first term has to be the bottom, not the derivative of the bottom, but the bottom. Which means this term has to be the derivative of the top. Minus vice versa. Unlike the product rule, where the order doesn't matter. Okay, I'm just going to go down these one for one. If you don't need to do this one, let me know.
Tangent of u squared equals g of u equals u. Yeah, this one we should probably do.
Okay. This is actually a pretty important concept in calculus. When you apply the chain rule and you take the derivative of the outside times the derivative of the inside, what you're doing is differentiating a composite function. Okay? So this f of g of u is a composite function. So let's first of all figure out what f of g of u is, and then we can take the derivative of it by taking the derivative of the outside times the derivative of the inside.
Okay, so
Now let me think about this as to whether we have to do this the hard way, or can we just take the derivative of this and multiply it by the derivative of that. Well, let's see what happens if we do that, rather than going about figuring out what that function is. I think this has to work. Let's see. Derivative, well, if f of u equals inverse tan of u squared, what does f inverse, or f prime of u equal?
that's the 1 over 1 plus u squared.
Which means 1 over 1 plus u to the fourth.
U to the fourth. Yeah.
And we still have to take the derivative of this inside. So I'm going to say that that's times 2u. Okay? So now let's figure out what g of u is. That is e to the u. So g prime of u is e to the u. So if my guess is right, the derivative of this is the derivative of the outside, which is the derivative of f of u, which is this, times the derivative of the inside, which is this. So hopefully we'll find an answer on there of 2u e to the u all over 1 plus u to the fourth. If we don't, we're going to have to do it the hard way.
That is an answer on that.
Yeah, number 2. Oops, oh, hold on. Which answer is that?
Oh, sorry, e to the fourth.
A.
No.
It's A.
Yeah, A. Sorry.
So that is kind of a shortcut as opposed to figuring out what the composite function is. In other words, notice that I didn't actually do that. I did not figure out what f of gu was. Had I could still have then just differentiated. But it might have been a little more complicated.
Yeah.
Because f of gu is going to be a more complicated function to take the derivative of. Notice I didn't have to apply a quotient rule here.
Yeah.
Whereas had I come up with f of gu, then I'm going to have to apply a quotient rule, and I'm going to have to end up differentiating something like that, which is going to be a lot harder. All right. Well, let's do this the same way. Oh, hold on. We can't do it the same way. It's not the same problem. This problem. Notice they don't give us f of x. They give us the derivative of f of x.
Yes, they do.
And they give us h of x. And they want the derivative of f of h of x. All right.
So, couldn't we do this since we already have the derivative of the outside, so the derivative of the outside would just be the g of x. And then the inside is sine x, so the derivative is negative cosine x, so then wouldn't it be g of x, not negative cosine, sorry, g of x cosine x times cosine x?
So B.
Or at least that's what I was thinking when I did this one.
That's probably correct. This is a section which is one of the more difficult calculus problems. And that is taking the derivative of composite functions. I'm looking for it in my book because there is an equation that we need. I guess we could figure it out. Let's see if we can figure it out. Oh no, that's inverse. This is different. Yeah, this is different. This is not the inverse. That's why I got confused for a moment thinking this was inverse. You're absolutely right. To take the derivative of f of h of x, I'm going to take the derivative of the outside, which is f prime, which we know is g of x, times the derivative of the inside, which is cosine x. So it's B.
Sure.
All right. Okay, when is a function increasing?
When the derivative is positive?
Yes. So let's take f prime of x and set it equal to greater than 0 and solve it.
So f prime of x. We'd have to do the product rule for that, right?
Correct?
So we have e to the negative x.
Well, one moment here. I would say that it makes sense to distribute this first before applying the product rule. In other words, let's make this read this. Because now we can do each of these separately. This one requires the product rule, but this one doesn't. And the derivative of the difference of two things is the difference in the derivatives. So let's find the derivative of that first. So now use the product rule on this part of it.
So we would have x squared times e to the negative x plus...
Hold on. Times the derivative of that, which is negative 1. In other words, the derivative of e to the minus x is minus e to the minus x.
Okay. And then
Take the derivative of the outside times the derivative of the inside. Okay. So that's the first half of the product plus 2x.
2x e to the negative x.
Okay. So we have that minus the derivative of this, which is what?
Negative 15e to the x, negative x.
Yeah, and the two negatives turn into a positive. In other words, when we take the derivative of that, we have a minus 15e to the minus x. Those two negative signs turn into this positive sign.
Yeah.
So this is f prime of x. So we're setting that equal to 0. So let's move this minus 15e to the minus x to the left side. We're going to leave everything else. You're going to see that we're going to be able to divide out an e to the minus x from every piece.
Yeah.
So that crosses with that and that. And what do we have left here? We have minus 15 equals, I'm going to factor out a x, minus x times x plus 2. And that is a quadratic, so you should have noticed that. So let's redo this. Let's put everything on the same side. So I've got x squared minus 2x minus 15 equals 0. How does that factor?
X minus 5x plus 3.
So my two solutions are x equal 5, x equal minus 3. Hold on a second. I set it greater. I set it equal to 0. Let's go back here. I got confused. Okay. We got to set this greater than 0. Right? It's only increasing when the derivative is greater than 0. So now we have to solve this inequality. And to do that, I use a line chart. You familiar with the concept of a line chart?
Yes.
Okay. What are my critical points?
Negative 3 and 5.
And if I test points to the left of negative 3, I get minus, minus, so those are all plus. If I check points in between, I get minus times a plus. And if I check points to the right, I get that. So my answer is x is wherever I'm seeing pluses. So x has to be greater than 5 or less than minus 3. B. Okay? Okay, we're going to implicitly differentiate this. So we have x squared plus 4y squared equals 7 plus 3xy. So we're trying to find dy dx. Okay?
Okay.
So let's start with the left side. What does this give me?
2x squared.
Just 2x. In other words, dy dx. I could follow this by a dx dx if I wanted, but it's not necessary.
Okay. Plus 8y dy dx
Just for
equals 0. plus 3 dy dx? Or,
Actually, 3y.
no,
In
3y?
other words, the first step of the product rule is the derivative of that times that. That's 3y. We're not yet taking the derivative of y, so I don't have to follow it with a y prime. In other words, this first step right here was strictly the derivative of 3x times y. Now I have to add to that 3x times the derivative of y. Well, the derivative of y is 1 y prime. Because now I am taking the derivative of y.
Mm-hmm.
Okay, so you with me?
Yeah.
Okay, what's the next step?
I can given by this.
Remember, we're
Moving
trying
yeah.
to solve for y prime. So
I would say moving the y primes both to the same side.
yes.
So.
And moving everything else to the other side. And the next step?
Solving for it, to factor out the y prime from that side. And then
Divide by that.
Dividing the whole thing by that.
And that should be what they wanted us to show. 3y minus 2x over 8y minus 3x. Part B. Show that there is a point P with x-coordinate of 3 at which the line tangent to the curve P is horizontal. Find the y-coordinate of P. Oh my God. There is a point with x-coordinate 3 at which the line tangent to P. So there's a point 3 comma y. So if this is my slope of this curve, at any point, and they're saying that at the point x equal 3, the tangent is horizontal, meaning what?
The slope is 0.
Yeah, so if I set m equal to 0 and solve this, I will get that point. And I'm going to substitute 3 for x.
Yeah.
I don't really care about the denominator because the only way that the slope can be 0 is if the numerator is equal to 0. So y equals 2.
Well, that's awfully easy.
Yeah. This isn't multiple choice, apparently?
No, this section is not.
Okay. All right. Let's see here. Figure out how to get this up a little higher. Find the value of the second derivative at the point found in part B. So what are we going to do here? This is the first derivative. That is dy dx.
So we're going to take the second derivative. We're going to differentiate that.
Well, right. We're going to differentiate this, and then we are going to substitute our point 3 comma 2 to answer the question. Find the value of the second derivative at the point we found in B. Well, the point we found in B was 3 comma 2. So there's the point. So we need D So we're going to differentiate this, and then we're going to substitute that point for x and y, and we're going to come up with a number.
Oh, fun.
Won't be that hard. Let's just do it step by step.
So we have to do the quotient rule. So first we have 8y minus 3x times 3 dy dx minus 2.
3y prime
Yeah. Minus 2.
minus 2. Hold on. Let me think about this a second. We're taking the bottom times the derivative of the top. The derivative of the top is 3y prime minus 2. Yeah. Okay, and then from that, we're going to subtract the opposite, which is the derivative of the bottom, which is what?
The derivative of the bottom is 8y prime minus 3.
Times the top.
Which is 3y minus 2x.
All of it's divided by the bottom squared. Okay, so now we have to substitute for our y prime, which is that. Probably the easiest way to do this is to figure out what y prime is based on these two numbers. What is this number here? And then I won't have to substitute this big long variable and plug everything in. Let's see, we got 6 minus 6. That number is 0. Y prime is 0 at that point. Oh, we knew that because the derivative was horizontal.
Yeah.
So we know y prime is 0, so all of these terms go to 0. And what are we left with here? We're left with 8y minus 3x times minus 2 minus a minus 3, so that's plus 3 times 3y minus 2x.
Yeah.
All over 8y minus 3x squared. Now we got to plug in 2 and 3. So what do we have here? Minus 2 times 16 minus 9 plus 3 times y was 2, 6, 0, all over 16 minus 9 squared, 49. So let's see, that's 7. Minus 2 times 7 is minus 14 over 49 minus 2 sevenths.
Yeah.
Okay, and the only difficulty of that problem is what to substitute for y prime when you get it. In other words, we ended up with 2 y primes. This was a y prime over here. And I could have gone back and substituted 3y minus 2x all over 8y minus 3x. That is y prime. That would have just made the algebraic expression that much harder to deal with. So instead of substituting that, I just figured out what y prime was at this point, and it was 0. So I substituted 0 for y prime, and then substituted 3 for x and 2 for y to come up with the complete answer. Okay, does the curve have a local maximum, a local minimum, or neither at point P? Justify your answer. What do we get for point P? We got -2/7. Now, what is something that has a single derivative of 0 at a point usually indicates that there's a maximum or a minimum there. It's not always. Sometimes you can have a 0 slope and not have a maximum. In other words, the slope right there is 0, but there's no min and there's no max. So, to determine whether we have a min or a max at a particular point, we look to the second derivative. There is what is called a second derivative test. If the second derivative is positive, it is concave up on the original function. If the second derivative is negative, it is concave down. Since this is negative, it is concave down, and it's therefore a maximum.
Okay.
If the second derivative is 0, you would have that situation where you have a horizontal, tangent line and you don't have a min or a max. So in this case, the second derivative wasn't 0. So we knew that there was a min or a max. It's just determining, the way I remember it is positive means opening up, but that means a minimum, and negative means opening down, and that means a maximum. So this is a maximum. And it would be neither if that second derivative was 0.
That makes sense.
Yeah, that would mean it was an inflection point. And second derivatives of zeros are inflection points, which are halfway. Notice that this point right here in my graph is an inflection point. And the inflection point is where it goes from being concave down to concave up. So if you get an inflection point of 0, or a second derivative of 0, that's an inflection point. And there is no minimum or maximum at that. Okay, this is a related rate problem.
There we go. That's the page.
I still got you?
Yeah, so I was flipping through my pieces of paper because I don't have them in order, so I was trying to find the page number 8 on it.
All right. Related rate problems are easier than they look. It is all about defining an equation, implicitly differentiating it, and then plugging in everything you know. So let's draw a picture. This ladder is 24 feet long. It's leaning up against a vertical wall. We have a little kid that's pulling the bottom of the ladder in that direction at 1 foot per second. Nice kid. So the information they've given us is what? They have given us a derivative. Notice they have given us a rate. When you see 1 foot per second, whenever you see a velocity, That is a rate. That is the first derivative of position. So they have basically, if I want to make this, let's set up a coordinate axis here. And I'm going to make this my x. So I'm going to call that x. I'm going to call that y. So what they have told me is that dx dt, the derivative of the horizontal movement with respect to time, is equal to -1 foot per second. And it's minus because I've set up a grid system here, and to the left is negative, to the right is positive. Up is positive, down is negative. Okay? What is the overall function that describes this model right here?
Would we just be using the Pythagorean?
Yes.
So that's x squared plus y squared equals 24 squared.
Now let's implicitly differentiate this thing for dy dt. So what is dy dt equal to?
We have 2x dy dt.
Actually 2x dx dt.
Oh yeah, sorry.
In other words, whenever we run into a variable that isn't t, we have to follow it with d, that variable, relative to t.
Yeah. Plus dy dt, or 2 dy dt, yeah, equals, that turns into a 0, so.
Okay. So now, notice that we know dx dt is -1. One moment here. Let's see what their first question is. How fast is the top of the ladder sliding down the wall when the foot of the ladder is 8 feet from the wall? So they're saying x is equal to 8, and they want us to solve for dy dt. Hold on one second. Wait a minute. Is there somebody out there? I have a person at 3 that's coming to my office, and I thought they might be out there. Okay, so we want to solve for dy dt, right?
Yes.
Hold on a second. Let's see. Did I do this properly? Yeah. Nah, this is, yeah, hold on. This is right. If I want dy dt, I do it exactly like this, okay. Now I can just fill in all the unknowns. Dy dt is equal to 2 times x, they're telling us, is 8. Dx dt is -1 plus 2 times y. Well, we got to solve for y. What is y if x is 8? If x is 8, is this a 3, 4, 5 triangle? No.
X is 8.
So y is the square root of 24 squared minus 8 squared. You got a calculator?
Yeah, I'm doing it right now. It's 24 squared minus 8 squared. Oh, it's divided. Oops. Oh, minus, not divided. So that's the square root of 512, about 22.
Yeah, I mean, I don't know what it is. We'll just leave it as the square root of 512. Times dy dt. Now I have one equation, one unknown. Something's not right, though. No, it's okay. It's okay. Yeah, no, we can solve it. So if I move all my terms with dy dt to one side, I'm going to subtract this over there. I'm going to factor out a dy dt. So dy dt times 2 times square root of 512 negative plus 1 equals minus 16. So dy dt equals whatever that number is. And is it positive or negative?
Don't the two negatives cancel and it's positive?
Yeah, it shouldn't be. It should be negative. Because it's slipping down. Let's see. Would it change much if I use plus 1 instead of minus 1? Changes only.
Fine.
It turns this into a plus 16 instead of a minus 16. And now dy dt is a minus number. I'm not comfortable with that answer. Seems to me they either both need to be negative or both need to be positive. It's possible that I make a math error here. Let's see. We got x squared plus y squared equals 24 squared. And when I implicitly differentiate to try to find dy dt, 2x times dx dt plus 2y times dy dt equals 0. So that is the case. How did I get to where I got here? I'm not quite sure how I got this. I screwed up somewhere. Let's go back to this step right here. If this is equal to 0, then dy dt is equal to minus 2x dx dt divided by 2y. Did I do that right this time? Let's see. This is equal to minus that and then divided by 2y. Yeah, so this is right here. And now this is what we're going to substitute everything in for. Not quite sure how I got off track, but I did. Here, let's... Okay, so we know that when x is equal to 8, y is equal to root 512. Why does 512 sound like that? That's 256. 256 is 16 squared. So this is 16 root 2 is y. So dy dt, we're trying to solve for it, y prime equals minus 2 times x, which is 8. I'm going to put that minus 1 in there again. Again, it's positive. All right. Well, pretty sure I did this correct. I'm not sure why I'm getting a positive number as opposed to a negative number. So this gives us 16 over 32, or 1 over 2 root 2, or root 2 over 4. That's the change in y.
Yeah.
How fast is the top of the ladder sliding down the wall when the top of the ladder is 16 feet from the ground instead of 8?
Wouldn't that just be solving it again, except for using a 16 to find your y? And
yeah, it would be. Yeah, it'd be. It's exactly the same, only x and y are different. Y is 16. X is the square root of 512 minus 256. So x is square root of 256, which is 16. 16. Yeah. In other words, when y is 16, x is 16. To make this, what was the ladder length?
24, I think.
So 24 squared, you said, was 512.
24 squared is 576.
Oh, okay. So all my numbers are wrong here. So y is...
y is the square root of 512.
Well, in our first answer...
Well, yeah, and the first answer was
5 square root of 576, right?
Yeah.
Because we had... No, because we subtracted 64 off of that. So
yeah, that was why it was 512.
It was 512, yeah. So y was 512 in the first case. And what is x in the second case? I've got the square root of 576 minus 256, which is 16 squared. So I got the square root of 320 is x. So we go back into this equation right there, and we figure out what it is with x being square root of 320, dx dt being 1, and y being 16.
That makes sense. I can do that.
Okay. Let's see if we can finish up this problem. Oh, gosh. Alpha. I knew they were going to put a toughie in there. Uh-oh. Hold on, let me get back to it. What problem are we on?
8. Oh, yeah, 8.
All right, this isn't that hard. C. So we're back to the original condition, which is x is 8, and y is root 512. And root 512 is 256 times 2, so that is 16 root 2. I don't have any problem writing it like that. And they want to know this angle. How fast is the angle between the top of the ladder and the wall? So they're talking about that angle right there. How is that changing? So let's define an equation that has theta in it?
We could...
What is the tangent of theta equal to?
Tangent, so opposite over adjacent, so 8 over 16 root 2.
So what is theta equal to?
Theta is... comes down to 1 over...
It's the inverse tangent of 8 over 16 root 2. They want d theta dt. Yeah. So what's the inverse tangent? What's the derivative of inverse tangent?
The derivative of inverse tangent is, well, the formula, it's 1 over 1 plus x squared, so it would be 1 over 1 plus that 8, 8 over 16 root 2 squared.
Right. Right. Actually not right. Let's go back here a step. Tangent of theta is x over y. So inverse theta is the inverse tangent of x over y. Now d theta dt, oh my goodness, it's 1 over 1 plus x over y squared times the derivative of the inside. Okay, the derivative of the inside, let's go through it. It's the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. So we want to take this and multiply it by that. That is d theta dt. And we happen to know everything. We know what dx dt is, we know what dy dt is, we know what x is, and we know what y is. So we can plug all of those things in to come up with a number for d theta dt.
Yeah.
That's a hard one. But not really. Not if you set up the basic equation, and then solve for theta, and then solve for d theta dt by implicitly differentiating this thing. Even though what you get is fairly complicated, we don't need to do all this algebra. We just need to plug in the value for x and y. We know x is 8. We know y is 16 root 2. We know dx dt is minus 1. And we know that dy dt is some value that we calculated somewhere back in here. I think dy dt was what? I can't remember what it was. But we figured out what it is. I think I erased it as part of what I erased. Anyway, Chase, I got to end it there because I got this student here.
Okay.
But I hope that's been helpful. That's a hard problem, but that's also an excellent problem. So that illustrates a whole bunch of things. So we can pick up from that next time.
Okay.
Okay? All right. Well, I guess not, huh? You're having your final here soon. If you need when is your final? What day?
I think it's Friday.
Next Friday?
Yeah.
Yeah, it has to be next Friday. If you feel like you need a session between now and next Friday, I've got time. I don't have a lot of time. My Thursday is, hold on, let me get to the right week here. That's this next week. Okay, that's what my week looks like. At 2 o'clock, I could see pretty much any day, Tuesday, Wednesday, or Thursday, or even Monday. Thursday is my most open day, if your test is on Friday. Okay? So let me know if you need another session, and I'll put it in. This session for Saturday, you don't need that one, right?
Yeah, I think that's safe to remove.
Okay. I will remove just that one. And then the following Saturday, I'll leave it on there until I hear otherwise.
Okay.
Okay? I mean, I'm not sure what your Christmas break looks like, whether you're going to want to keep working on calc during the break or what, but I'll let you let me know. So at the moment, we don't have an appointment until the 28th.
Okay.
Okay? All right, Chase. Have a good one.
Thank you.
Bye-bye.